Torque control with joint position and velocity limits avoidance. This paper is accepted for the IEEE International Conference on Robotics and Automation in London. A large variety of control algorithms have been developed for controlling a robotic system to perform the desired motion. Though, the control algorithm is applicable and safe for the robotic system if it satisfies the robot's physical constraints including the motion and actuation limits. In this paper, we propose a torque control algorithm for fully actuated manipulators which ensures the joint position and velocity limits of the robot. The general torque control architecture for robotic systems could be summarized as you see. In this architecture, the controller receives the desired and current trajectory of the robot as input and generates the desired joints, torques or forces as the output that is passed to the robot motor's controller. Considering this architecture, for ensuring the joint limits of the robotic system, various techniques have been presented in the literature like optimization-based approaches, barrier Lyapunov functions, state transformation techniques, and heuristics approaches. But a control method that ensures the asymptotic stability of the desired trajectory along with the joint limits avoidance for both the position and velocity of the robotic system is missing. For this, we propose a control method based on the state transformation technique. In this technique, we use a map that transforms the constrained joint space into an unconstrained space. Then, we design a controller in the unconstrained space for tracking the desired trajectory. With this technique, we ensure that the desired trajectory is globally asymptotically stable, and we also ensure that the time evolution of the joint position and velocity remains always within the associated limits. The key point in our proposed technique is the mapping from the constrained joint space to the unconstrained space. For this, we use the hyperbolic tangent function. In this regard, we define the joint position as Q average plus delta Q multiplied by tangent hyperbolic of S1. The same, we also define the joint velocity as Q dot average delta Q dot multiplied by tangent hyperbolic of S2. S1 and S2 are new states. In this way, if S1 and S2 are bounded, then Q and Q dot are within their associated limits. With this mapping, we transform the constrained dynamics of the robotic system which is written with respect to joint position and velocity to an unconstrained dynamics written with respect to new states S1 and S2. Moreover, if S1 and S2 are stable and track the corresponding desired trajectory, then Q and Q dot satisfy the limits while tracking the desired trajectory. With this unconstrained dynamics, the control approaches proposed in the literature could be used for controlling the robot for performing the desired motion. We used the feedback linearization approach in our paper. We evaluated our proposed control architecture in some simulations in humanoid robot iCub. For this, we simulated the controller and the robot in MATLAB Simulink and Gazebo, respectively. The controller and robot are communicated through YARP channels. In this simulation, we control 3 joints of the right leg of iCub, namely the hip pitch, hip roll, and knee while the robot is installed on the pole. The joints are expected to follow a harmonic trajectory. The 3 above and below figures show the position and velocity trajectory for the 3 controlled joints. As you can see, the joint trajectories converge to the desired values while respecting the joint limits in the both position and velocity level. We also evaluated the robustness of our proposed control technique in the presence of some disturbances. For this, we control the robot's right leg for converging to a desired configuration. During the motion, a vertical force is applied to the robot's right foot. As can be seen, the joint trajectories try to converge to the desired value while respecting the associated joint limits despite of the disturbance force. In some time instances, the knee velocity passes the upper limit because of the disturbance, but the controller adjusts very well the velocity and aligns it to the limit range. Let's take a look at the desired joint torque generated by our proposed controller, for example, the joint torque for the hip roll in harmonic motion. At the beginning of the simulation, the joint torque spikes in some time instances which is harmful to the actuators of the real robot. Considering the position and velocity of the hip roll, we see that these spikes happen when the joint velocity is close to its limits. In fact, these spikes are the results of the discrete implementation of the controller. We could reduce these effects by using higher frequency implementation. However, in the real world, the controller frequency is limited by the hardware limitations. So, as our future work, we plan to improve the performance of our proposed controller in discrete implementation. Thanks for watching this video. If you are interested in the details of our work, please check the paper and code.